All right, so for today's lab, we're going to be talking about springs and Hooke's law. So Hooke's law describes the basic action of a spring, and springs are very, very important in all sorts of cases, and especially if you're doing any sort of engineering. Almost every single material you'll work with has some sort of a spring-like features to it, depending on the applied force. Sometimes you can ignore them. Sometimes you have to take them into account. So springs work on basically two principles. They can usually either be in extension or in compression. And I've got sort of an image of that here. We've got your regular spring. If you apply force to close it, that's compression. If you apply force to pull it, that's extension. Now, the springs we'll be working with in this lab are all going to be in extension, although both styles of spring action are very important to consider. Now, a spring usually has two functions. It can either apply or counteract force, and I'm sure you've seen this where you want to sort of smooth the motion of your car, for instance. That's why you have those coil springs to smooth the influence of a bumpier road surface from the interior of the car. The other action a spring will have is to store energy. We actually saw this in lab 3 when we had projectile motion. We had to compress a spring to store some energy to launch that ball bearing. So that's a spring storing energy later to release it. Now, spring behavior is dictated by Hooke's law. Hooke's law basically says that the force of a spring is equal to the negative spring constant times the displacement. This negative is very important because basically what it's saying is that the spring will counteract the displacement you put upon it. So when you try to push that spring towards a positive x value, it's going to want to push it away to a negative x value, or vice versa. Negative x will try to push to positive x. So that's why that's a negative sign. Now, K is the spring constant. That basically tells you how strong the spring is and how hard it is to compress it or extend it. And that's a unit that's, the units of the spring constant are usually expressed in newtons per meter, or some variant of that, sometimes, pounds per inch, if we're going to be using silly units, right? So bring it a little closer so we can investigate how that spring constant changes with how you set up your spring. So when you have more than one spring, you have to take into account how the two springs interact with one another. So if you have two springs in a row like this is called a series of springs. And it's a slightly complicated equation. You have to take the total spring constant of the two of them together is 1 over that is equal to the sum of the inverse of each of the spring constants. That's not going to be something you're familiar with yet, but you'll use it a lot, especially in the next level physics 208, where it's going to be very useful for resistors in parallel. Basically, the effect of this is, however, is that when you line two springs up in a row, the spring constant is actually less than the individual spring constants of each spring. So how that works more or less is that you no longer, to move it 1 meter, you no longer have to move each of the springs 1 meter themselves. So it becomes easier to extend or compress those springs. Now, in parallel, it's a simpler picture. The total spring constant is simply the sum of the individual spring constants. And this maybe makes a little more sense. You can imagine we have to use 5 newtons to pull this 10 centimeters and 5 newtons to pull this one 10 centimeters. So if you have to pull the entire ensemble 10 centimeters, you have to pull each of them 10 centimeters so the forces add up. So it's a much simpler picture and something that will probably be a little more intuitive than the series picture. So consider that when we're doing our lab, because we'll be working with both series and parallel sets of springs.